Welcome to the Drowsy Astronaut, where we explore the cosmos at a pace designed for rest, one gentle detail at a time. And tonight, we contemplate one of the strangest ideas in physics, the white hole. What happens when the universe flips its own rules? A place that stands opposite to the black hole itself, where everything that would fall in is instead cast out. Light, matter, and even time spilling back into space. This is going to be a long journey, not through space, but through theory, and you can listen straight through, drift in and out, or fall asleep whenever your thoughts begin to fade into the quiet. Whether you're here to relax, to learn about something fascinating and calming, or simply to rest, just know that you are exactly where you need to be. And as you already know, that I love hearing from you all, what you think about tonight's topic and where you're tuning in from. Whether you're under clear skies or city lights, in bed, at work, or somewhere peaceful between the two. Drop a comment if you're comfortable sharing, and without further ado, let us begin. So let's start with what we know with black holes, objects we have detected, studied, and now even photographed. And from there, we will explore their mathematical opposite, the white hole. Black holes are regions of space where gravity is so strong that nothing can escape, not matter, not light, not even information according to some interpretations of quantum mechanics. They form when massive stars collapse at the end of their lives, when the core implodes under its own gravity, creating a singularity, a point of infinite density surrounded by an event horizon. The event horizon is the boundary, the point of no return, where the escape velocity exceeds the speed of light, and anything crossing it is pulled inexorably toward the center, never to return. Let's take a moment to understand black holes more deeply, because understanding them will help us understand white holes later, and black holes themselves are fascinating objects, worth contemplating as you relax tonight. Imagine a star, a massive one, perhaps 20 times the mass of our Sun, burning brightly for millions of years, converting hydrogen to helium in its core through nuclear fusion, releasing tremendous energy that holds the star up against gravity. The star lives in balance, gravity trying to crush it inward, and the pressure from nuclear reactions pushing outward, and these two forces balance each other, keeping the star stable for most of its life. But eventually, after millions of years, the star runs out of fuel, the nuclear reactions stop, and there is nothing left to hold the star up against gravity. And what happens next determines the star's fate. For stars, like our Sun, the collapse is gentle. The core shrinks down to become a white dwarf, about the size of Earth but with half the Sun's mass, and the outer layers are expelled into space, forming a beautiful planetary nebula. But for much more massive stars, the collapse is catastrophic. The core implodes in less than a second, and the collapse is so violent that it triggers a supernova explosion. One of the most energetic events in the universe, briefly outshining entire galaxies. If the collapsing core is massive enough, nothing can stop the collapse, not even the pressure from neutrons, and the core continues to shrink, becoming smaller and smaller, denser and denser, until it becomes a black hole. At this point, the core has collapsed past its Schwarzschild radius, the size at which the escape velocity equals the speed of light, and the event horizon forms around it, marking the boundary from which nothing can escape. Inside the event horizon, space and time behave in ways that seem impossible. A According to general relativity, time and space actually swap roles, so that moving forward in time inside a black hole means moving inward in space. And you cannot stop this motion any more than you can stop time itself from passing. This is why nothing can escape a black hole once it crosses the event horizon, because escaping would require moving backward in time, which the laws of physics do not allow. From outside the black hole, watching someone fall in, you would see them slow down as they approached the event horizon, moving slower and slower, and their light would be redshifted, becoming dimmer and redder until they fade from view. But from the perspective of the person falling, nothing special happens at the horizon. They cross it smoothly, experiencing nothing unusual at the boundary, though they are now doomed to reach the singularity at the center, where they will be torn apart by tidal forces. The singularity is the ultimate mystery, a point where our equations predict infinite density and infinite curvature of space-time. And these infinities tell us that our theories break down here, that we need new physics, perhaps quantum gravity, to understand what really happens at the center of a black hole. Black holes are not just theoretical, we have detected them in many ways. By watching stars orbit invisible companions, by detecting gravitational waves when black holes merge, and by imaging the shadow they cast against glowing gas using the Event Horizon Telescope. The image from the Event Horizon Telescope was remarkable, showing a dark circle surrounded by a bright ring of light, exactly as Einstein's equations predicted. And this confirmed that black holes exist and behave as general relativity describes. Black holes come in different sizes, from stellar mass black holes, a few times the mass of the Sun, to supermassive black holes at the centers of galaxies, millions or billions of solar masses. And these giants shape the evolution of entire galaxies through their gravity. Now that we understand black holes, at least in outline, we can begin to imagine their opposite, the white hole, and to understand what this strange theoretical object would be like if it could exist. Picture a black hole in your mind, the dark shadow at its center, surrounded by glowing gas spiraling inward, matter and light falling in, never to return. And this one-way flow is the defining characteristic of a black hole. Everything goes in, nothing comes out. Now imagine reversing this, flipping the arrow of time, and you get a white hole where matter and light come out, nothing goes in. And the event horizon becomes a boundary you cannot cross inward instead of a boundary you cannot cross outward. This sounds impossible, and it probably is in our universe, but it is a mathematical solution to Einstein's equations. And exploring this impossible idea will help us understand gravity, time, and the nature of reality more deeply, even if white holes never actually exist. So rest now. Let the image of a black hole settle in your mind. The dark center, the glowing accretion disk, and know that we are about to explore its opposite, something strange and beautiful, even if it only exists in equations. And let this gentle contemplation carry you towards sleep. Einstein's equations of general relativity describe how gravity works, how mass and energy curve space-time, and how objects move through that curved space following paths called geodesics. And these equations are beautiful in their symmetry and elegance. One remarkable feature of these equations is that they work in both directions, forward in time and backward in time. And this symmetry means that for every solution describing matter falling into a black hole, there exists another solution describing matter coming out of a white hole. This mathematical symmetry is called time reversal symmetry, and it appears in many fundamental laws of physics, suggesting that the equations themselves do not distinguish between past and future, at least not at the most basic level of description. If you take a black hole solution and reverse the direction of time, you get a white hole solution, an object that expels matter and light instead of consuming them. And mathematically, this solution is just as valid as the black hole itself. To understand this better, let's think about symmetry in physics and what it means for equations to work in both directions of time, and why this does not mean we see time running backward in everyday life. Imagine filming a simple event like a ball rolling across a smooth table, and then playing the film backward, and you would see the ball rolling in the opposite direction, but the motion would still look natural because the laws of motion work the same way, backward and forward in time. This is what physicists mean by time reversal symmetry. The fundamental equations do not care which direction time flows, and both directions produce valid solutions that obey the same mathematical rules. But now imagine filming something more complex, like a cup falling off a table and shattering, and playing that backward, and you would see the fragments flying together, assembling into a cup, and leaping back onto the table, which looks unnatural and never happens in reality. The difference between these two examples is entropy, a measure of disorder, and the second law of thermodynamics says that entropy always increases over time, and this gives time a direction, an arrow that points from past to future. Simple systems like a rolling ball have low entropy and can behave symmetrically, but complex systems like shattering cups have high entropy and show a clear direction in time, always moving toward greater disorder. Black holes and white holes are both solutions to Einstein's equations, but they differ in their entropy behavior, and this is one reason why black holes exist, but white holes probably do not. And we will explore this idea more deeply as we continue. For now, just know that the equations allow white holes mathematically, but the universe prefers black holes because of the way entropy works, and this tension between mathematics and physics is what makes white holes such an interesting thought experiment. The white hole solution was discovered by physicists studying Einstein's equations, and it appears naturally when you consider all possible solutions to the equations, not just the ones that seem physically reasonable to us. A white hole is essentially a black hole running backward in time, where the collapse that created the black hole is reversed, becoming an explosion that expels matter and energy outward, and the event horizon becomes a boundary that nothing can cross inward. In the white hole solution, matter and light emerge from the center, streaming outward through the event horizon. And once outside, they travel away, and nothing from the outside universe can ever fall in. The boundary repels everything that approaches. This might sound like an explosion, and in some ways it is, but it is a very specific kind of explosion. One governed by the same space-time curvature that creates black holes, just reversed in the direction time flows. Imagine standing at a safe distance from a white hole, watching it, and you would see matter and light continuously flowing outward, streaming away from the event horizon, and the white hole would shine brightly, the opposite of the dark shadow a black hole casts. You could approach the white hole, moving closer and closer, but you would find it impossible to reach the event horizon because the space-time curvature would push you away, and the closer you got, the stronger the repulsion would become. This is the mirror image of a black hole, where approaching the event horizon becomes easier and easier until you cross and can never escape. But with a white hole, reaching the horizon becomes harder and harder until it becomes impossible. The mathematics describes this clearly, but it raises an obvious question. If white holes are valid solutions to Einstein's equations, why do we not see them anywhere in the universe? And the answer involves understanding how these objects would behave in reality. Time reversal symmetry is fascinating but also subtle, because while the fundamental equations work in both directions, the universe itself clearly has a direction, an arrow of time that we all experience. We remember the past, not the future. We see causes leading to effects, not effects leading to causes, and we see entropy increasing, disorder growing, and this gives time its direction. White holes violate this natural direction of time because they represent matter and energy flowing from the future into the past, at least from a certain mathematical perspective, and this is one reason they probably cannot exist in our universe. But the fact that the equations allow them is interesting, because it tells us something about the symmetry of physical laws, and it gives us a different perspective on black holes, helping us understand them better by contrast. Rest here for a moment, let these ideas settle, and do not worry if they seem strange or confusing, because white holes are strange by nature, and even physicists find them difficult to grasp fully. The important thing is not to understand every detail, but to appreciate the beauty of the mathematics, the symmetry of the equations, and the fact that exploring impossible things can teach us about the possible things, about black holes and gravity and the nature of time itself. So breathe slowly, let your mind rest on these concepts, and know that we will continue exploring white holes gently, building up the picture slowly, and you can drift in and out of sleep as we go. The story will continue whether you are awake or dreaming. The event horizon is the key to understanding both black holes and white holes. It is the boundary, the surface of no return, and understanding how it works will help us see the difference between these two objects. For a black hole, the event horizon is a one-way membrane. Things can cross it going inward, but nothing can cross it going outward. And once you are inside, your fate is sealed. You will reach the singularity at the center. The event horizon is not a physical surface. It is not made of anything. It is simply a mathematical boundary in space-time, the location where the escape velocity equals the speed of light, and this makes it a point of no return. From outside the event horizon, you can still escape a black hole's gravity by firing your rockets and flying away, though the closer you are to the horizon, the more energy you need to escape. But once you cross the event horizon, escape becomes impossible, not because the gravity is stronger, but because of the way space-time is curved, and inside the horizon, all paths lead to the singularity, and there is no path that leads back outside. This is hard to imagine, but think of it this way. Inside the event horizon, trying to escape the black hole is like trying to avoid tomorrow. It is not a matter of having enough power. It is that all futures lead inward, and there is no future in which you escape. The event horizon of a white hole works exactly the opposite way. It is a boundary you cannot cross inward, but things can cross it outward. And this creates a very strange situation, a region of space you can never enter no matter how hard you try. Imagine approaching a white hole from outside, flying toward it in your spaceship, and you would find that the closer you get, the harder it becomes to make progress, as if the space itself is pushing you away. The mathematics shows that reaching the event horizon of a white hole would require infinite energy and infinite time, and so you can never actually get there. You can only get closer and closer, asymptotically approaching, but never reaching the boundary. This is the mirror image of what happens with a black hole, where reaching the singularity is inevitable once you cross the horizon, but with a white hole, reaching the horizon from outside is impossible, and you are always kept at a distance. Meanwhile, From inside the white hole, matter and light are flowing outward, streaming through the event horizon and emerging into the outside universe. And once they cross the boundary, they can never go back inside. The horizon repels them forever. This creates a situation where the inside and outside of a white hole are causally disconnected, just like with a black hole, but in the opposite way, the inside cannot receive information from outside, and the outside cannot send information inward. If you could somehow be inside a white hole, looking outward, you would see the entire future of the outside universe compressed into a moment because of the way time behaves near the horizon. From inside, the event horizon would appear as a glowing boundary, beyond which lies the outside universe, and you would see matter and light streaming outward through the horizon, escaping into the external space. But you could never stay inside. If you exist inside a white hole at all, you would be expelled outward, forced through the event horizon and into the outside universe, and this is what white holes do. They expel everything inside them. The mathematics is clear, but the physics is problematic, because if white holes expel everything, where does that matter come from? And how does it end up inside the white hole in the first place? And these questions point to the fundamental problem with white holes existing in reality. Time near the event horizon behaves strangely for both black holes and white holes. And understanding this will help us see why white holes are so different from anything we experience in everyday life. For a black hole, time slows down as you approach the event horizon from outside. And if you watch someone falling in, you would see them slow down, their movements becoming slower and slower, and they would appear frozen at the horizon, never quite crossing from your perspective. For a white hole, time behaves oppositely as matter approaches the event horizon from inside, ready to be expelled. Time speeds up from the perspective of an outside observer, and the matter would appear to accelerate, bursting outward through the horizon in a sudden rush. This time distortion is part of what makes white holes so strange. They seem to violate our intuition about cause and effect, about how things flow from past to future, and this violation is why most physicists believe they cannot exist in our universe. Rest now with this image in your mind, a boundary you can never cross, matter flowing outward, time behaving strangely, and do not worry about understanding every detail, just let the strangeness wash over you. White holes are called impossible objects for a reason. And part of the beauty is in contemplating something that our universe does not allow, something that exists in mathematics but not in reality. And this contemplation can be peaceful, like imagining a dream that can never come true. The event horizon of a white hole is a mirror image of a black hole's horizon. And by understanding this mirror, we understand black holes better, we see them more clearly, and we appreciate the strangeness of gravity and space-time more deeply. So let your mind rest on this boundary, this impossible surface, and let the idea settle as you relax, knowing that we will continue the journey gently, exploring where white holes might come from, if they could exist at all. If white holes could exist, where would they come from? And this is one of the biggest problems with the white hole idea, because unlike black holes, which form from collapsing stars, there is no obvious process that would create a white hole. Black holes have a clear origin story. A massive star runs out of fuel, its core collapses, and a black hole is born. And this process is well understood. And we have observed supernova explosions and detected the black holes they leave behind. But white holes are the opposite. They expel matter rather than forming from collapsing matter. and there is no natural process we know of that would create such an object. And this is the first hint that white holes probably do not exist. Still, physicists have proposed a few speculative ideas for where white holes might come from, if they exist at all, and exploring these ideas is interesting even if none of them are likely to be correct, because they push our understanding of physics to its limits. One possibility is that white holes could be remnants from the Big Bang, objects that formed in the early universe when conditions were extreme and different from today. And this idea was popular for a while, but has largely fallen out of favor. In the very early universe, shortly after the Big Bang, space-time was extremely curved, matter and energy were incredibly dense, and strange things might have happened, processes that do not occur in the universe today. Some physicists speculated that white holes could have formed in this chaotic environment, perhaps as regions where the Big Bang's expansion was especially violent, creating objects that expelled matter outward. Like mini explosions frozen in space-time. If such objects formed, they would be ancient, about 13.8 billion years old, and they might still exist today, scattered through the universe, though we have never detected any evidence for them despite decades of searching. The problem with this idea is that white holes are unstable, as we will explore in detail later. And even if they formed in the early universe, they would likely have destroyed themselves quickly, perhaps within fractions of a second, leaving nothing behind. Another idea is that white holes could form from quantum tunneling, a process where a black hole spontaneously transforms into a white hole through quantum effects. And this idea comes from attempts to understand quantum gravity, the physics that governs space-time at the smallest scales. In quantum mechanics, particles can tunnel through barriers that classical physics says are impossible to cross, and perhaps black holes could tunnel through some kind of barrier and emerge as white holes, though the details of how this would work are unclear. This idea is highly speculative, and most physicists do not think it is correct. But it is an interesting thought experiment, and it highlights how little we understand about what happens to black holes at the quantum level. A third idea involves wormholes, hypothetical tunnels through space-time that connect two different regions of the universe, or even two different universes. And in this picture, a black hole and a white hole would be the two ends of a wormhole. Imagine falling into a black hole, traveling through a tunnel in space-time, and emerging from a white hole in a different part of the universe. And this is a popular idea in science fiction, though it is almost certainly impossible in reality. The mathematics of general relativity does allow wormhole solutions, but these solutions require exotic matter with negative energy density to hold the wormhole open. And we do not know if exotic matter exists, and most physicists think it probably does not. Even if wormholes could exist, they would be unstable, collapsing almost instantly unless something holds them open, and anything trying to travel through them would likely be destroyed. So, this idea is more fantasy than physics, at least with our current understanding. Another speculative idea is that white holes could form when you reverse the process of black hole formation, imagining a star that explodes instead of collapses, but this does not actually create a white hole. It just creates a supernova, a normal explosion that we see frequently in the universe. A true white hole is not just an explosion, it is a region of space-time with specific properties, an event horizon that nothing can cross inward, and matter flowing outward from a singularity. And no natural process we know of produces this structure. The closest thing to a white hole that might exist is the Big Bang itself, which we will explore in a later section, the idea that the entire universe emerged from a singularity, expanding and expelling matter, and in some ways this resembles a white hole, though the analogy is not exact. But individual white holes, small objects like stellar mass or supermassive ones, have no known origin, and this is a strong indication that they do not exist, that they are purely mathematical solutions that our universe does not allow. So we are left with a mystery. White holes are predicted by mathematics. But we cannot imagine how they form, and this suggests that something is wrong, either with our understanding of the equations or with the assumption that mathematical solutions must correspond to physical reality. Physics is full of mathematical solutions that do not exist. Equations can produce all sorts of results, but only some of them match what we see in the universe. And the job of physicists is to figure out which solutions are real and which are merely mathematical curiosities. White holes probably fall into the latter category, mathematical curiosities that teach us about the equations but do not exist in reality. And accepting this is part of understanding the difference between pure mathematics and physical science. But exploring where they might come from is still valuable, because it pushes us to think about extreme conditions, about the early universe, about quantum gravity, and about the limits of our current theories. And this exploration can lead to new insights even if white holes themselves never materialize. Rest now with these speculative ideas, let them float through your mind, and do not worry about which ones are correct, because none of them probably are. And the value is in the exploration, not the destination. White holes remind us that the universe is stranger than we imagine, that mathematics can predict things that do not exist, and that understanding why something cannot exist is often as important as understanding what does exist. So let your mind wander through these possibilities: Big Bang remnants, quantum tunneling, wormholes, and let the ideas blend together as you drift towards sleep, knowing that we will continue exploring white holes gently, questioning whether they could even survive if they did exist. Time is one of the strangest aspects of white holes, and to understand them fully, we need to think about how time behaves near these objects, and why this behavior makes them so different from anything we experience in everyday life. Near a black hole, time slows down from the perspective of an outside observer. And this effect, called time dilation, is a prediction of general relativity that has been confirmed by many experiments and observations. If you watched a clock falling toward a black hole, you would see the clock tick more slowly as it approached the event horizon, and at the horizon itself, time would appear to stop. The clock frozen, and this effect is real, not an illusion. But near a white hole, time behaves oppositely. And this is where things become truly strange, because from an outside observer's perspective, time would appear to speed up near a white hole, and matter emerging from the event horizon would seem to burst outwards suddenly, accelerating as it escapes. To understand this, we need to think about what time really is, and how gravity affects the flow of time. And this will help us see why white holes are so problematic from a physical standpoint, even though the mathematics allows them. Time is not absolute. It does not flow at the same rate everywhere. According to general relativity, time flows more slowly in strong gravitational fields. And this has been measured, confirmed, and is even accounted for in GPS satellites that orbit Earth. Near a black hole, the gravitational field is extremely strong, and time slows down dramatically, and this effect becomes infinite at the event horizon, meaning time stops from the perspective of an outside observer watching something cross the boundary. But this does not mean time stops for the person falling into the black hole. From their perspective, time flows normally. They cross the horizon in finite time, and they continue falling toward the singularity without experiencing anything strange at the boundary itself. White holes reverse this situation, and if you could watch matter emerging from a white hole, you would see time behaving strangely, perhaps seeing the matter appear to accelerate, to rush outward. And the closer to the horizon it got before emerging, the more sudden its appearance would seem. This suggests that white holes and time are fundamentally incompatible, or at least that they require time to run backward in some sense. And this is deeply problematic because we never see time running backward in nature, except in carefully controlled quantum experiments at microscopic scales. The arrow of time, the direction from past to future, is one of the most fundamental features of our universe, and it is enforced by the second law of thermodynamics, which says that entropy, or disorder, always increases, never decreases, giving time its direction. White holes seem to violate this arrow. They seem to require entropy to decrease, for disorder to spontaneously become order, and this is why most physicists believe white holes cannot exist, because they contradict the second law of thermodynamics. Imagine watching a film of a black hole forming. You see a star collapse, matter falling inward and a black hole forming, and this process increases entropy, increases disorders, and is consistent with the second law of thermodynamics. Now play that film backward, and you see matter flying outward, a star reassembling, and what you are watching resembles a white hole. But this process decreases entropy, decreases disorder, and violates the second law, and this is why it never happens in nature. The second law is not just a suggestion, it is one of the most ironclad rules in physics, and every process we have ever observed obeys it. Entropy always increases or stays the same, never decreases in isolated systems. White holes, by their nature, would violate this law, because matter emerging from a white hole would need to be highly ordered, and this order would have to come from somewhere, from some source of low entropy, and we cannot identify such a source. This is perhaps the strongest argument against white holes. Not that the mathematics is wrong, but that the physics forbids them, that the universe has rules beyond the equations of general relativity, rules about entropy and the arrow of time. And these rules make white holes impossible. But thinking about time running backward is still valuable, because it helps us understand what time is, why it has a direction, and what role entropy plays in shaping our experience of reality. Time is not just a coordinate in space-time. It is something with direction, with flow, and this flow is determined by thermodynamics, by the tendency of systems to move toward greater disorder. And white holes would reverse this flow, which is why they probably cannot exist. So white holes are, in a sense, objects that would require time to run backward, and since time does not run backward in our universe, at least not on macroscopic scales, white holes remain mathematical curiosities, beautiful but impossible. Rest here for a moment, let these ideas about time settle, and do not worry if they seem abstract or difficult, because time itself is one of the deepest mysteries in physics, and even experts struggle to fully understand it. The important thing is to appreciate the strangeness, the fact that white holes challenge our understanding of time, and that exploring them helps us see why time has a direction, why we remember the past but not the future, and why broken cups do not spontaneously reassemble. White holes are impossible because time has an arrow, and that arrow points from past to future, from low entropy to high entropy, and anything that tries to reverse this arrow, like a white hole, is forbidden by the laws of physics as we understand them. So breathe slowly, let your mind rest, and know that we will continue exploring white holes gently, next imagining what they would look like if they could exist, and why their appearance would be so different from black holes. If white holes could exist, what would they look like from a distance? And this is a fascinating question, because imagining their appearance helps us understand how different they would be from black holes, even though the mathematics describes them as mirror images. Black holes are dark, they are literally black, because they trap light, and the Event Horizon Telescope showed us the shadow of a black hole, a dark circle surrounded by a bright ring of glowing gas. And this image confirmed what theory predicted. But white holes would be the opposite. They would not be dark. They would be bright, shining intensely as matter and light stream outward from their event horizons. And they would be visible across vast distances, like beacons in space, if they existed. Imagine approaching a white hole in a spaceship, and you would see a glowing sphere, matter and energy flowing outward in all directions, and the closer you got, the brighter it would appear, though you could never actually reach the event horizon no matter how hard you tried. The brightness of a white hole would depend on how much matter it was expelling, and if it was expelling matter rapidly, it would shine with incredible intensity, perhaps outshining entire galaxies. And this brightness would make white holes easy to detect if they existed, which is another reason we believe they do not. Astronomers have searched the sky for objects that might be white holes, looking for sources of light and matter that cannot be explained by known processes, and they have found nothing. No evidence for white holes, no mysterious objects that match the theoretical predictions. This absence of evidence is significant because if white holes existed and were as bright as theory suggests, we would have detected them by now. And the fact that we have not found them after decades of searching strongly suggests they do not exist. But let us imagine for a moment that we could see one and picture what the sight would be like, because the visualization helps us understand the theoretical properties, even if the object itself is impossible. From a distance, a white hole might look like a star, a bright point of light, but as you got closer, you would notice strange things, matter streaming outward in all directions, not orbiting or spiraling like around a black hole, but flowing straight out, escaping into space. The matter would be moving fast, perhaps close to the speed of light, and it would carry tremendous energy, and any spacecraft trying to approach would be battered by this outflow, pushed away by the force of the escaping material. The event horizon itself would be hard to see, because it would be hidden behind the outflowing matter. But you would know it was there, somewhere inside the bright glow, a boundary that you could never reach no matter how much power your engines provided. If you tried to fly toward the white hole, you would find your progress slowing. Not because of anything physical blocking you, but because of the way space-time is curved, the geometry itself pushing you away, making it impossible to reach the horizon. The appearance would also depend on the motion of the matter being expelled, whether it came out uniformly in all directions or in jets or in some other pattern. And the mathematics does not fully specify this, leaving some uncertainty about the exact appearance. But regardless of the details, the white hole would be bright and active, the opposite of the dark shadow of a black hole, and it would stand out in the cosmos as something unusual, something that defies expectations if it existed. One curious feature is that white holes would not have accretion disks, because matter cannot fall into them, and so you would not see the beautiful spiraling disks that make black holes so visually striking in artistic renderings and astronomical images. Instead, you might see an expanding shell of matter, material that was recently expelled, spreading outward, cooling and dissipating as it moves away from the event horizon. And this shell might glow with the heat of its recent expulsion from the extreme environment. The spectrum of light from a white hole would be interesting, because the matter being expelled would be incredibly hot, heated by compression and gravitational energy, and it would emit light across the spectrum, from radio waves to X-rays, with the peak depending on the temperature of the expelled material. If the white hole was expelling matter that had been near the singularity, that matter might be extremely hot, billions of degrees, and it would emit intense high-energy radiation, gamma rays and X-rays, and this radiation would make the white hole visible across the entire observable universe. But this brightness would also be a problem, because where is all this energy coming from? And this question brings us back to the fundamental issue. White holes have no source of matter or energy, and their existence would violate energy conservation unless they were created with all their matter already inside, which raises more questions than it answers. Astronomers have catalogues of bright, mysterious objects, gamma-ray bursts, quasars, magnetars, and many other exotic phenomena, but none of them match the predicted properties of white holes, and this absence of matches is telling, suggesting that white holes do not exist. If you could somehow get close enough to see details without being destroyed by the outflow, you might notice time behaving strangely, clocks running at different rates depending on how close they were to the horizon, though the exact behavior would be the opposite of what happens near a black hole. Near a black hole, time slows down as you approach the event horizon, but near a white hole, time would behave differently, perhaps appearing to speed up for matter emerging from the horizon, though the mathematics of this is subtle and depends on your perspective. The view from the white hole itself, if you could be inside looking out, would be even stranger. You would see the entire future of the universe compressed because of the way light travels in curved space-time, and you would be expelled outward through the horizon whether you wanted to be or not. But of course, you could never actually be inside a white hole, because they almost certainly do not exist. And even if they did, being inside one would be lethal. The extreme conditions near the singularity would destroy any matter, any structure, anything that tried to exist there. So the appearance of a white hole is a thought experiment, imagining what something would look like if the laws of physics allowed it, and this exercise helps us understand black holes better by seeing them in contrast to their impossible opposite. The darkness of black holes becomes more meaningful when we imagine the brightness of white holes. The inward flow of matter becomes more significant when we imagine the outward flow, and the stability of black holes stands out when we consider the instability of white holes. And that instability is what we will explore next. The fact that white holes, even if they could form, would destroy themselves almost instantly. And this instability is perhaps the strongest reason to believe they do not exist, that they are mathematical ghosts with no place in physical reality. Rest now. Picture the bright, glowing white hole, matter streaming outward, light pouring into space, and know that this vision is a dream, a mathematical dream, beautiful but impossible, and let that impossibility be peaceful rather than frustrating. White holes face a fundamental problem. They are unstable, and even if they could form somehow, they would destroy themselves almost instantly, and this instability is one of the strongest arguments against their existence in the real universe. To understand this instability, we need to think about what happens when anything disturbs a white hole. Even the smallest perturbation, the tiniest bit of matter or radiation approaching the event horizon, and the mathematics shows that such disturbances would cause the white hole to collapse or explode. Imagine a white hole floating in space, minding its own business, and a single photon, a particle of light, approaches the event horizon from outside. And you might think nothing would happen because the photon cannot cross the horizon inward, the boundary repels it. But the presence of the photon still affects the space-time around it, and this tiny disturbance creates ripples in the curvature, and these ripples propagate, growing larger, and eventually they destroy the white hole, causing it to collapse into a black hole or explode in some other catastrophic way. This instability is built into the mathematics of white holes, and it has been studied extensively by physicists, and the conclusion is always the same. White holes cannot exist in any realistic universe because they are too unstable to survive even for a moment. The problem is related to the direction of time, because white holes require entropy to decrease, and this is inherently unstable. Like a ball balanced on top of a hill, the slightest push sends it rolling down, and there is no way to keep it balanced in real conditions. Black holes are stable. They are like balls sitting at the bottom of a valley, and small disturbances do not change them fundamentally. They might cause ripples or waves, but the black hole remains, settling back into equilibrium after the disturbance passes. But white holes are like balls on hilltops, and any disturbance, no matter how small, pushes them off balance. And once off balance, they collapse or transform into something else, probably a black hole, which is the stable configuration. The universe is not empty. It is filled with radiation, the cosmic microwave background, starlight, cosmic rays, and countless photons traveling through space. And any white hole would be bombarded by this radiation constantly, disturbed continuously, and would collapse immediately. Even if you tried to create a white hole in a perfect vacuum, it would still be unstable due to quantum effects, because in quantum mechanics, empty space is not truly empty. It is filled with virtual particles that pop in and out of existence, and these virtual particles would disturb the white hole and cause it to collapse. So white holes are unstable for fundamental reasons, not just practical ones, and this instability means they cannot exist in our universe, not even for a fraction of a second, not even in the emptiest regions of space far from any stars or galaxies. This is a strong argument, perhaps the strongest, and most physicists consider it conclusive. White holes are mathematical solutions that physics forbids, and we should not expect to ever find one, no matter how carefully we search. The instability also affects ideas about white holes connecting to black holes through wormholes, because even if such a connection could exist, the tiniest disturbance would cause it to collapse, severing the connection and destroying both the white hole and the wormhole. Some physicists have tried to imagine ways to stabilize white holes, using exotic matter with negative energy, or using quantum effects to somehow counteract the instability, but these ideas are highly speculative and probably impossible, and there is no evidence that such stabilization is possible. The mathematics allows white holes, but nature does not, and this is a good lesson about the difference between pure mathematics and physical science. Equations can produce all sorts of solutions, but only some of them match what actually exists in the universe. White holes are beautiful mathematically. They demonstrate the symmetry of Einstein's equations, but they are unphysical. They violate stability requirements and they cannot survive in the real world. And accepting this is part of understanding how science works. Instability is not just a technical detail. It is a fundamental statement about what can and cannot exist. And it teaches us that not everything the equations allow is physically possible. There are constraints beyond the equations, constraints from thermodynamics, from quantum mechanics, and from the structure of reality itself. White holes fail these constraints. They are too unstable, and this is why we do not see them and why we should not expect to. And this conclusion is actually reassuring. It means our understanding of physics is consistent, that different branches of science agree with each other and point to the same conclusions. So rest easy knowing that white holes are impossible. Not because we have failed to understand them, but because we understand them well enough to see why they cannot exist, and this understanding is a triumph of science, not a failure. Let the concept of instability settle in your mind. Picture the ball on the hilltop, ready to roll down at the slightest touch, and know that this is why white holes remain in the realm of mathematics, beautiful but forever out of reach. Wormholes are another fascinating theoretical construct, and they are often discussed together with white holes, because in some mathematical solutions, a black hole and a white hole are connected through a wormhole, forming a bridge through space-time. This idea comes from Einstein and Rosen, who found a solution to Einstein's equations that describes a black hole connected to a white hole through a tunnel in space-time. And this solution is called an Einstein-Rosen bridge, though it is more commonly known as a wormhole. In this picture, you could fall into a black hole, travel through the wormhole, and emerge from a white hole in a different part of the universe, or even in a different universe altogether. And this is a staple of science fiction, though it is almost certainly impossible in reality. The mathematics allows wormholes just as it allows white holes, but the physics is problematic, and most physicists believe that wormholes, like white holes, cannot exist in any realistic universe, at least not in a form that anything could travel through. The first problem with wormholes is that they are unstable, even more unstable than white holes, if that is possible. And any wormhole would collapse almost instantly. Faster than light could travel through it, making it useless for travel or communication. The collapse happens because of the energy density inside the wormhole. According to general relativity, maintaining a wormhole requires exotic matter with negative energy density, and this exotic matter would need to fill the throat of the wormhole, holding it open against the tendency to collapse. Negative energy density is a strange concept. It means less than empty space, and while quantum mechanics allows negative energy in very specific situations on very small scales, it is not clear that enough negative energy exists to hold a macroscopic wormhole open. Most physicists believe that exotic matter cannot exist in large quantities, and therefore wormholes cannot be stabilized, and they would collapse immediately. And even if you could create one, you could not use it for travel, because it would collapse before anything could pass through. The second problem is, even if you could stabilize a wormhole, it would not actually connect a black hole to a white hole in a useful way, because the event horizons would still prevent travel through the connection. In the Einstein-Rosen bridge solution, the black hole event horizon is a boundary you cannot cross outward, and the white hole event horizon is a boundary you cannot cross inward. And these two boundaries meet inside the wormhole, forming a blockage that prevents anything from passing through. So even in the mathematical solution, you cannot travel through the wormhole. You would be stuck inside, unable to reach the white hole side, and the wormhole is not traversable. It is just a geometric structure in space-time that connects two regions without allowing travel between them. For a wormhole to be traversable, you would need to modify the geometry, perhaps using exotic matter to create a different kind of connection, and physicists have proposed various schemes for doing this, but all of them require exotic matter and are probably impossible. Some physicists have speculated about quantum wormholes, tiny wormholes at the Planck scale, smaller than atoms, much smaller than anything we can directly observe, and these might exist as quantum fluctuations in space-time, constantly forming and dissolving. These quantum wormholes would be far too small to travel through, and they would exist for incredibly brief times, fractions of a second, so small they are almost meaningless, but they might play a role in quantum gravity in understanding how space-time behaves at the smallest scales. But these speculative quantum wormholes have nothing to do with the science fiction idea of traveling through a wormhole to distant parts of the universe. That idea remains firmly in the realm of fantasy, not physics, at least with our current understanding of the laws of nature. Wormholes, like white holes, are mathematical solutions that probably do not exist, and even if they did exist, they would not be useful for travel or communication, and they would be unstable and collapse almost instantly. And this is the consensus among physicists who study these things. The connection between black holes and white holes through wormholes is an interesting mathematical structure, and studying it teaches us about the geometry of space-time, about how Einstein's equations work, and about the limits of what is possible. But it does not mean that such connections exist in reality, and it certainly does not mean we can use them for anything. And this is another example of the difference between mathematical possibility and physical reality. So while wormholes and white holes are fun to think about, and they appear in countless science fiction stories, we should not expect to find them in the universe, and we should not expect to ever travel through them. And this is not a limitation of our technology, but a fundamental feature of physics. Rest now with these ideas, let them float through your mind, and do not worry about wormholes or white holes being real. They are ideas, mathematical dreams, and sometimes dreaming about impossibilities is peaceful, knowing that the universe has limits, that not everything imaginable can exist. Quantum mechanics adds another layer to the white hole story, and some physicists have explored whether quantum effects might allow white holes to exist in ways that classical physics does not, or whether black holes might transform into white holes through quantum processes. One interesting idea involves Hawking radiation, the prediction that black holes slowly evaporate, losing mass over incredibly long periods of time through quantum effects near the event horizon. Stephen Hawking showed that quantum mechanics allows particle pairs to form near the event horizon, with one particle falling into the black hole and the other escaping, and from outside, this looks like the black hole is emitting radiation, slowly losing mass and energy over time. This process is incredibly slow for large black holes. A black hole, the mass of the Sun, would take longer than the current age of the universe to evaporate completely, and supermassive black holes would take far longer, but eventually, given enough time, any black hole would evaporate away to nothing. The question is what happens at the very end, when the black hole has lost most of its mass and is down to a tiny remnant, perhaps the size of a subatomic particle. And some physicists have speculated that at this final moment, the black hole might transform into a white hole, briefly expelling whatever remained inside before disappearing completely. This is a highly speculative idea, and it comes from attempts to understand quantum gravity, the physics that would govern space-time at the Planck scale, the smallest scale where our current theories break down and new physics is needed. In some approaches to quantum gravity, particularly loop quantum gravity, the singularity at the center of a black hole might be replaced by a bounce, a quantum transition that converts the collapsing matter into expanding matter, effectively transforming the black hole into a white hole. This transformation would happen at such small scales and involve such extreme conditions that we cannot test it with current technology, and most physicists consider it speculative, an interesting idea, but far from proven or even strongly supported by evidence. If this transformation could happen, it would only occur at the end of a black hole's life, after trillions upon trillions of years of evaporation, and the resulting white hole would be tiny, subatomic, and would last for only an instant before expelling its contents and disappearing. So even if quantum effects allow black hole to white hole transitions, these would not be the macroscopic white holes we have been discussing. They would be quantum objects too small to see, too brief to detect, and irrelevant to the question of whether white holes exist in any meaningful sense. The idea is interesting because it suggests a way to resolve the black hole information paradox, the question of what happens to information that falls into a black hole and whether that information is destroyed or somehow preserved, which is a deep problem in theoretical physics. If black holes transform into white holes at the quantum level, then the information might not be destroyed but expelled during the transformation, and this could resolve the paradox. But, again, this is highly speculative, and most physicists do not think this is the solution. Quantum white holes might also appear as fluctuations in space-time, tiny wormholes or white hole structures forming and dissolving constantly at the Planck scale, and these would be part of the quantum foam that physicists imagine fills empty space at the smallest scales. But these fluctuations would be incredibly small, billions of times smaller than an atom, and they would exist for incredibly short times, so brief that light could not travel across them before they disappeared, and they would have no observable effects on the macroscopic world. These ideas push the boundaries of physics. They explore what might happen in regimes we cannot yet test, where quantum mechanics and gravity both become important, and where our current theories give contradictory or incomplete answers. But they do not change the conclusion that macroscopic white holes, objects that could be detected by telescopes or that could affect the universe in observable ways, almost certainly do not exist, because the instability and entropy arguments still apply at larger scales. So quantum mechanics adds interesting possibilities, but does not rescue white holes. It suggests that tiny, fleeting quantum white holes might exist as part of space-time structure, or that black holes might briefly become white holes at the end of their lives. But these are not the white holes of science fiction or of the classical mathematics we have been discussing. The distinction between quantum and classical is important here, because many things are possible at quantum scales that are impossible at macroscopic scales, and white holes may fall into this category, quantum curiosities that have no macroscopic counterparts. Rest now with these quantum ideas, let them blend with your dreams, and do not worry about understanding every detail, because quantum gravity is one of the biggest unsolved problems in physics, and even experts do not fully understand it yet. The important thing is to appreciate the layers. Classical white holes are impossible due to instability, but quantum white holes might briefly flicker in and out of existence at scales we cannot observe by, and this layering of possibility and impossibility is part of what makes physics beautiful and mysterious. One of the most intriguing ideas about white holes involves the entire universe, the possibility that the Big Bang itself was a white hole, and that the expansion we see around us is matter and energy being expelled from this cosmic white hole. This idea has a certain appeal because the Big Bang does resemble a white hole in some ways, a singularity from which matter and energy emerged, expanding outward, and everything we see in the universe today came from that initial outburst about 13.8 billion years ago. In the 1960s and 70s, some physicists explored this analogy seriously, asking whether the universe could be modeled as a white hole, and whether this would help explain the origin and evolution of the cosmos. The mathematics showed some similarities, but also important differences, and over time, the idea fell out of favor as cosmologists developed better models of the Big Bang based on inflation and quantum field theory. And today, almost no one thinks the Big Bang was literally a white hole. The problem with the idea is that white holes and the Big Bang behave differently. White holes have event horizons that nothing can cross inward, but the Big Bang did not have such a boundary, at least not one that affects us today, and matter in the universe can move freely, not constrained by the geometry of a white hole event horizon. Additionally, the expansion of the universe is not like matter being expelled from a single point. It is more like space itself expanding, carrying galaxies along with it. And this is a fundamentally different process from matter streaming outward through space-time. The Big Bang singularity, the moment when the universe began, is similar to the singularity in a white hole. Both are points where our equations break down and predict infinite density. But this similarity does not mean they are the same kind of object. And cosmologists have developed other ways to understand the Big Bang. Modern cosmology uses the theory of inflation, which proposes that the early universe underwent a brief period of exponential expansion driven by a quantum field, and this inflation explains many features of the universe we observe today, including its large-scale uniformity and structure. Inflation does not involve white holes. It is a different kind of process, and it has been tested through observations of the cosmic microwave background. The afterglow of the Big Bang and the predictions of inflation match the observations remarkably well, giving us confidence that this model is at least approximately correct. So, while the Big Bang was a singular event, an emergence of matter and energy from an extremely dense state, it was not a white hole in the sense we have been discussing, and the analogy breaks down when you examine the details carefully. Some physicists have explored bouncing cosmologies, where the universe goes through cycles of expansion and contraction, with each contraction reaching a minimum size and then bouncing back into expansion. And in these models, the bounce might resemble a white hole transition from a collapsed state. But these bouncing cosmologies are speculative. They require quantum gravity to describe the bounce, and they have not been confirmed by observations, so they remain interesting ideas rather than established science. The connection between white holes and cosmology is mostly historical, an interesting idea that physicists explored but that did not lead anywhere. And today, cosmologists use different models to understand the Big Bang and the evolution of the universe. But the fact that people considered the idea seriously shows how physicists think. They take mathematical solutions seriously, they explore analogies and connections, and they test these ideas against observations. And when the ideas do not match reality, they move on to better models. White holes as cosmological objects failed this test. They do not match what we observe, and they do not explain the features of the universe better than other models. So cosmologists have moved on, though the idea remains in the history of the field as an interesting might have been. So the universe is not a white hole, and the Big Bang, while mysterious, is better understood through other frameworks. And this is progress. This is how science works. Testing ideas and keeping the ones that work while discarding the ones that do not. Rest now knowing that the universe is not a white hole. It is something even more interesting, an expanding cosmos with a history we are gradually uncovering through observations and theory, and the story of the universe is richer and stranger than any single analogy can capture. Let the idea of the Big Bang settle in your mind, not as a white hole, but as the beginning of time and space, an emergence from a state we do not fully understand, and know that scientists are working to understand it better, slowly piecing together the puzzle of cosmic origins. Some physicists have not given up on white holes entirely, and they continue to explore alternative theories where white holes might play a role, particularly in approaches to quantum gravity that modify general relativity at very small scales. One such approach is loop quantum gravity, which treats space-time as fundamentally discrete, made of tiny loops rather than smooth continuous fabric, and in this framework, the singularity at the center of a black hole might be replaced by a quantum bounce. In loop quantum gravity, when matter collapses to form a black hole, it does not collapse to infinite density, but instead reaches a maximum density set by quantum effects, and then bounces, beginning to expand again, and this bounce would transform the black hole into a white hole. This transformation would happen inside the event horizon, hidden from outside observers, and the black hole would continue to appear normal from outside, but inside, the collapsing matter would bounce and begin trying to escape, though it would be trapped behind the event horizon. Eventually, after an incredibly long time, the event horizon might dissolve, or quantum effects might allow it to disappear, and at that point, the white hole region inside would be revealed, briefly expelling the matter before the entire structure evaporated. This is a complex scenario, and it is highly speculative based on a theory of quantum gravity that has not yet been confirmed by experiment, and most physicists consider it an interesting possibility, but far from proven. The timescales involved would be enormous, far longer than the current age of the universe. And so, even if this process happens, we would never observe it directly. We could only detect it through very subtle effects, perhaps through studying the final moments of evaporating black holes. Another alternative theory involves the idea of Planck stars, quantum objects that form at the center of black holes when matter is compressed to the Planck density, the maximum density allowed by quantum mechanics, and these objects might eventually explode outward, creating white hole behavior. These ideas push physics to its limits. They involve regimes where both quantum mechanics and general relativity are important, where our current theories give incomplete or contradictory answers, and where new physics is needed, and scientists are working hard to develop these new theories. But it is important to be clear about the status of these ideas. They are speculative, they are not proven, and they may turn out to be wrong when we finally develop a complete theory of quantum gravity. The fact that physicists continue to explore white holes in these contexts shows that the idea has not been completely abandoned, but it has been relegated to the extreme edges of speculation, to quantum gravity and regimes we cannot yet test experimentally. For practical purposes, for understanding the universe we observe today, white holes do not exist. They are not part of the landscape of astrophysics, and we do not need them to explain anything we see, and this is unlikely to change even if quantum gravity eventually confirms some limited role for white hole processes at microscopic scales. So alternative theories keep the white hole idea alive, but only barely, and only in forms very different from the classical white holes we have been discussing. And the consensus among physicists remains that macroscopic white holes do not exist and probably cannot exist. The exploration continues because physicists are curious, because quantum gravity is an unsolved problem, And because understanding extreme situations helps us understand normal situations better, even if the extreme situations never actually occur in nature. This is the nature of theoretical physics, exploring possibilities, testing ideas against mathematics and observation, and gradually narrowing down what can and cannot exist. And white holes have mostly been narrowed out, classified as mathematical curiosities rather than physical realities. But the process of exploring them has been valuable. It has taught us about black holes, about time, about entropy, and about the limits of our theories, and this knowledge is worth having even if white holes themselves do not exist. Rest easy, knowing that the universe is understandable, that physicists are working to understand even the strangest possibilities, and that white holes, whether they exist or not, have helped us understand the cosmos better. Let these alternative theories float through your mind like dreams: quantum bounces, Planck stars, loop quantum gravity, and do not worry about which ones are correct, because the value is in the exploration, not in any single answer. The universe is full of mysteries, and white holes are just one of them. A mystery that probably has a simple answer: they do not exist. But asking the question and exploring the possibilities has enriched our understanding of everything else. We return now to where we began, to the question of white holes, and after this long, gentle journey, we can see them for what they are: mathematical solutions that probably do not exist in physical reality, but that teach us something valuable nonetheless. White holes are impossible, most likely, because they are unstable, because they violate the second law of thermodynamics, because we have never detected them despite searching, and because the universe prefers black holes, which are stable and consistent with the arrow of time. But the impossibility does not make them worthless. Studying white holes has helped us understand black holes better, by contrast, by seeing what happens when you reverse time, by exploring the mirror image and appreciating the original more deeply. White holes remind us that mathematics can describe things that do not exist, and that physics imposes constraints beyond the equations, constraints from thermodynamics, from quantum mechanics, and from the structure of reality itself. And understanding these constraints is as important as understanding the equations. The study of white holes is a perfect example of theoretical physics at work, taking mathematics seriously, exploring all possibilities, and then testing them against reality. And when reality says no, accepting that answer and moving on, but keeping the lessons learned along the way. We learned about time, about how it has a direction imposed by entropy, about how black holes warp space-time, about event horizons and singularities, and about the difference between mathematical possibility and physical reality. And all of this knowledge came from thinking seriously about white holes. Science advances through this process, asking questions, exploring possibilities, and gradually narrowing down what exists. And white holes have been narrowed out, but the process of exploring them was worthwhile. It deepened our understanding of everything else. There is a lesson here about imagination and reality, about how we can imagine many things that do not exist, but that imagining them helps us understand what does exist. And this process of imaginative exploration constrained by observation is what makes science so powerful and so beautiful. White holes are beautiful ideas, even if they are impossible. They demonstrate the symmetry of Einstein's equations. They show us what time reversal would look like, and they give us a mirror to hold up to black holes. And beauty in mathematics is valuable even when it does not correspond to physical reality. Many of the most beautiful ideas in physics are like this: perfect symmetries that are broken in nature, ideal solutions that are modified by real-world complications, and mathematical elegance that nature chooses not to implement. And appreciating this beauty is part of being a scientist or a curious person. We study impossible things because it helps us understand possible things. And because the boundary between possible and impossible is not always clear until we explore it. And sometimes what seems impossible turns out to be real, and other times what seems possible turns out to be forbidden. White holes fall into the forbidden category, but exploring that boundary has been valuable. And if we ever develop a complete theory of quantum gravity, we may understand even more clearly why white holes cannot exist, and that understanding will be another step forward. So as you drift towards sleep tonight, let these ideas settle, let the image of white holes fade, and appreciate that you have contemplated something at the edge of possibility, something strange and beautiful, even in its impossibility. The universe is full of wonders, both real and imaginary, and black holes are among the real ones. Objects so strange they almost seem impossible themselves, but they exist. We have detected them, and they are part of the cosmos we inhabit. White holes are the imaginary counterparts, the impossible mirrors, and thinking about them has helped us appreciate black holes more deeply, understand time more clearly, and see the universe with greater wisdom and wonder. There is peace in this, in knowing the universe has limits, that not everything we can imagine exists, and that understanding what cannot exist is as important as understanding what can, and this knowledge brings a kind of completeness to our picture of reality. Science is not just about discovering new things. It is also about understanding why certain things do not exist, why certain processes cannot happen, and these negative results are just as valuable as positive discoveries because they define the boundaries of possibility. White holes have taught us these boundaries. They have shown us that time has a direction, that entropy always increases, that stability matters, and that mathematical beauty does not always translate into physical reality. And these lessons enrich our understanding of everything else. So rest now, peacefully, knowing that white holes are impossible, and that this impossibility is not a failure but a feature, a sign that the universe is consistent, that physics works, and that we can understand it. Let your mind wander now between waking and sleeping, and think of black holes as they really are, dark and patient, slowly evaporating over unimaginable timescales, and shaping galaxies with their gravity. Think of time flowing forward, always forward, entropy increasing, disorder growing, and the arrow of time pointing inexorably from past to future, giving structure to our lives and meaning to our experiences. Think of the universe expanding, carrying galaxies apart, and know that this expansion is not a white hole, but something else, something even stranger, an unfolding of space itself, driven by forces we are still working to understand. And think of yourself here on Earth, made of atoms forged in stars, thinking about impossible things and finding peace in contemplation. And this is a beautiful thing, this capacity to imagine beyond what exists, and to understand why some imaginings must remain forever in the realm of dreams. The cosmos is vast and full of mysteries, but it is also knowable bit by bit, and white holes, though they do not exist, have played their part in our journey of understanding, and we are grateful for the lessons they taught us along the way. So, sleep well, dream peacefully, and let the strange beauty of white holes fade into the background, where they belong in the realm of mathematics, of thought experiments, and of impossible things that help us appreciate the possible things more deeply. Tomorrow, the universe will still be here, black holes will still exist, time will still flow forward, and entropy will still increase, and you can wake refreshed, knowing that the cosmos makes sense, that physics works, and that impossible things remain safely impossible. Good night, and may your dreams be filled with wonder, with black holes and stars, with time and space, and with the peaceful knowledge that some mysteries have answers, even if the answer is that something beautiful cannot exist. Thank you for traveling with me tonight, through the strange world of white holes, from mathematics to impossibility, and I hope you found something calming, something fascinating, or simply a moment of peace in contemplating these ideas. White holes will always be there in the equations, waiting for anyone who wants to explore them, but they will never be in the sky, never be detected. And this is exactly as it should be, because the universe knows what it is doing. Until next time, rest well, let the stars watch over you, and remember that understanding why something cannot exist is just as beautiful as discovering what does exist, and both kinds of knowledge bring us closer to truth. Good night, and may your sleep be deep and peaceful, filled with dreams of the cosmos, where black holes exist but white holes do not, and where time flows gently forward, carrying us all toward tomorrow.